Hi everyone, it's Mr. Hamilton here. This video is about trig ratios for angles from 0 degrees to 360 degrees. It's the cast rule. There are always going to be, for any trig ratios, two possible angles between 0 and 360. So we're going to understand what this diagram tells us and then how to apply it. So the first thing we need to understand is some terminology. For any angle theta, notice this is the angle theta there, we're always drawing that from the positive x-axis in a counterclockwise direction around the terminal arm. That terminal arm is the arm that is turning around the axes. For any angle greater than 90 degrees, the values of the primary trigonometric ratios are either equal to or negative of the ratios of the related acute angle. The related acute angle is this value right here, and that is always measured to the x-axis, whatever distance is or whatever angle is shorter. So if you're down here in this quadrant, you're going to measure it here. If you're down here in this quadrant down here, you're going to measure angle beta there. And if you're in this quadrant, beta there. If you're in the first quadrant, the related acute angle and beta are going to, the related acute angle beta and the principal angle theta are going to be the same. But in every other quadrant, theta is always measured from the x-axis around, and beta is measured just from the x-axis, whether it's the positive side or the negative side. So when we solve for angles greater than 90 degrees, in which we have an angle here that's greater than 90, or if we had theta that continued around here, that would be an angle bigger than 90, or all the way to this fourth quadrant, that would be an angle bigger than 90 as well. When we do that, we use the related acute angle to find the related trigonometric ratio and solving things from there. So let's look at what the cast rule means. The cast rule helps us determine which trig ratios are positive in each quadrant. And what you can see here is we have quadrant 1, 2, 3, 4 in a counterclockwise direction around from 0. But the cast rule doesn't start in quadrant 1. The cast rule starts in quadrant 4, 1, 2, 3. The reason for that is if we actually started in quadrant 1, we'd have the ASTC rule or the AST rule, which is kind of weird. So the way they say it is the cast rule, simply to keep it a word that makes sense in the English vocabulary, if you will. Obviously, though it's not a word, it stands for something. So let's see what that actually stands for. In the first quadrant, we can see that it stands for all. So what that means is that all the trig ratios are positive. So let me use a 45-degree angle as an example. This side here would be simplifying to ratios of 1, 1, and root 2. If you didn't see my video on 5.2 special triangles, then you check that out to see why that happens. But regardless of what triangle I draw, it will always simplify to those ratios if it's a 45-degree angle and a 90-degree triangle. And so what we get is for all the ratios, they always end up positive. So sine would be 1 over root 2, that's positive. Cosine would be 1 over root 2, that's positive. And tan would be 1 over 1, that's positive. And that would apply to any other things for the same reasons, right? The y value is positive, the x value is positive, and then the r value, which is the length of the terminal arm, note that the r is the length of the terminal arm, is also positive. That's always going to be the case in that quadrant. They're always going to be positive, so all of the trig ratios are going to be positive. Now, if we took that angle, I'm just going to erase what I've got there, and I'm going to draw the same thing now in the second quadrant. If I draw the same thing in the second quadrant, now my related acute angle is 45 degrees, because that related acute angle is always measured down to the x-axis. But my principal angle is measured all the way around from 0 to that. And so that's going to be a principal angle of 135 degrees. Now you'll notice here that the x value is going to be negative because we're in the negative x part of the graph. And so if I simplify that x value is going to simplify down to negative 1 when we set up the ratios. The y value is going to simplify down to positive 1, and the r value is going to simplify to the square root of 2. Again, the r value being the length of the terminal arm, always going to be a positive value. It's only the x and y that could be positive or negative. Now, because this is 45 degrees, that's why the ratios simplify down to that. Obviously, if we used a different angle like 30 or 60 or any angle, any related acute angle of 30 or 60, or any angle in that second quadrant, we're going to get different numbers for the sides, But what I'm interested in here is what the ratio's signs are, positive or negative. And so if you look in this quadrant, if you look at sine, we take sine of the angle. Sine of 45 might be something, but we're looking specifically sine of the principal angle, 135. So sine of 135, I'm just going to put that in for theta. Sine of 135 is the opposite side, which is 1, over the hypotenuse, which is root 2. That is a positive ratio. Well, what about cosine of 135? Cosine of 135 is the adjacent side, which is negative, over the hypotenuse. That gives me a negative 1 over root 2. That is a negative ratio. And if you do the same thing for tan of 135, the opposite, which is 1 over the adjacent, which is negative 1, we get 1 over negative 1. That is also a negative sign. So the only one that's positive in that second quadrant is sine. And so that's the whole idea here. The only one that's positive there is sine. I could use the same things to show you that the only one that's positive in this quadrant, quadrant 3, is tan. And so that's why we have T for tan being positive in quadrant 3. And then for quadrant 4, I could do the same thing to show you that the cosine ratio is the only one that's positive in quadrant 4. So again, any angle that's in those quadrants won't have the same ratios as I've shown you there, because I've shown you specifically for a related acute angle of 45, but will have the same signs. All are positive in quadrant 1, quadrant 2, just sine is positive, quadrant 3, just tan is positive, and quadrant 4, just cosine is positive. So if you were given only the primary trig ratio and asked to find the angle, how many answers are there for each ratio? Well, there's going to be 2. Let's go back and look here for a minute at this. If I have a 45-degree angle, this side is length 1, this side is length 1, this side is length root 2, and the ratios of those are always going to simplify to that, then I can tell you that cosine of 45 degrees would be 1 over root 2. Now, we could rationalize the denominator, and ideally we should, but I'm not going to do that here just for the purpose of what I'm trying to show you. For cosine, it's also positive in quadrant 4, and so this would give me a negative 1 as the y value, the x value is still 1, and the r value is still root 2. And so if I just show you that here, then cosine, this angle, if this related acute angle is 45, then that means the principal angle all the way around, this theta angle, is going to be 360 minus 45. That's going to be an angle of 315 degrees. And so if that principal angle is 315 degrees, then cos of 315, well, cos is the adjacent over the hypotenuse, 1 over root 2. And so you can see here that if I gave you a ratio of 1 over root 2, what answer is it? Is it 45 degrees or is it 315 degrees? Well, the correct answer is it's both. Your calculator, however, will give you the only one of those angles. And so you have to determine based on the cast rule what second answer is possible. Here, for a 45-degree angle and its cosine, it would be cosine of 315 degrees. So let's now consider the same initial 45-degree angle in a different quadrant and just see how this works out. Instead of cosine, what if I gave you sine of 45 degrees? Sine of 45 degrees. If I give you sine of 45 degrees, well, we know that that is going to be the y value, or the opposite over the hypotenuse, so it's 1 over root 2. Well, where else is sine positive? Sine is positive in the second quadrant, and that's because if I drew my related acute angle here, 45 degrees, in the second quadrant, then I'd have 1, negative 1 down here, and root 2, because the x value is negative 1. And so what I'm going to do here is, if I calculated sine here, sine of what angle? Well, that angle would be 180 minus 45. So 180 degrees minus 45 degrees, that would be a principal angle of 135 degrees. So sine of 135 is also 1 over root 2. So if I gave you sine of 45 as 1 over root 2, the other angle would be 135 degrees. Both of those angles are correct for that ratio. The last one we'll look at is the tan. So if I gave you instead tan of that, let's look at what that would be. Just erase a few things here so we have some clarity of what that would look like. If I gave you tan of 45 degrees, well, you would tell me that's the opposite, which is 1 over 1. And if I gave you, we would say that because tan is also positive in this third quadrant, well, let's look at this here. The y value is -1, and the x value is -1 for a related acute angle of 45 degrees. So that means the principal angle is 180 plus 45 degrees. Remember that related acute angle is always, always, always measured just to the x-axis, never the y-axis. So that would give me a principal angle of 225 degrees. And so you can see here, if I calculate tan of 225, well, that's going to be -1 over -1. That's going to make it +1, which is the same thing as I had over on the other first quadrant. And so that would tell me that if I knew that the tan of 45 was 1, that the other angle possible would be 225 degrees. Now, your calculator will never tell you both answers. It will always tell you one of them. And if it ever is an answer in this quadrant, your calculator will definitely not tell you that. Your calculator is designed and set up in such a way that it will always give you an angle down here between -90 degrees, because if I go on a clockwise rotation from the x-axis, that's -90. And if I go on a counterclockwise rotation to 180 degrees. So it will give you some angle between -90 and 180. And then you have to interpret it into the other quadrant for what the cast rule says. So let's just set up these ratios so we understand what each sine, cos, and tan and their reciprocal ratios actually are. So the first thing to note here is that sine of any angle is equal to the y value over the r value. It's the opposite, which is the y, over the r value. And so cosine would be the adjacent over the hypotenuse, which is the x value over the r value. And tan would be the opposite over the adjacent, which is the y value over the x value. Cosecant is just the reciprocal of sine, so that's r over y. Secant is the reciprocal of cos, so that's r over x. And cotangent is the reciprocal of tan, which is x over y. So we're going to use those ratios to solve the next two examples together. The one thing I want to add here before I do that is that the related acute angle is this angle here. And in terms of sine, cos, and tan of those, what those are always going to be is we're always going to make those positive ratios. So sine of the related acute angle is the positive value of y over r. R is always positive, so we're not going to worry about making the positive of that. The signs there, those lines just mean the absolute value. In other words, take the positive part of it, don't worry about the sign being positive or negative. The cosine would be the absolute value of x over r, and the tan would be the absolute value of y over the absolute value of x. And I'm going to show you why that's useful in the end of the first example. So let's look at the first example together here. It says here, example 1, the point -4, 3 lies on the terminal arm of theta in standard position. So -4, 3. If we're to sketch that, -4 would be somewhere over here. 3 would be somewhere up here. So this is -4, 3. So that point is lying on the end of the terminal arm in standard position. It doesn't say the end, but if they give you a point, assume it's at the end. This is -4 and 3. So what that means, if I put that there, I'm just going to put the -4 down here so we can label the sides better. That means that the y value is 3, and it means that the x value is -4. And then the r value, well, you can probably guess it based on knowing your 3, 4, 5 triangles, but I'll show you how to calculate that in a minute if you don't. That's all we know so far. That's part A. We've sketched the angle. Now for part B, it says determine what the r value is. Well, the r value, we use the fact that it's a 90-degree triangle, and we use the Pythagorean theorem to solve that. So a squared plus b squared equals c squared. Well, what are we dealing with here? We're actually dealing with the x, y, and r. And so in terms of any angle here, we can call this instead x squared plus y squared equals the r squared value. And so the x squared value is -4 squared. Notice I'm putting the negative in brackets. because I'm concerned about lengths. I don't want the negative to interfere with anything. So very important you put that in brackets. So negative 4 squared plus 3 squared equals r squared. This is 16 plus 9. That gives you r squared, which is 25. And so that tells you that r is the square root of 25, which is 5. Now, some of you might think, well, couldn't I take the positive and the negative square root of that? And you absolutely could. And that's what we do when we take the square root. We always take the positive and negative square root. But because it's the r value, it can only ever be positive because it's the length of the terminal arm. And a length of the terminal arm is only ever positive. So we ignore the negative in this case. Ignore negative since it's the r value. If it was the x or the y value that we were calculating, we'd have to then interpret based on the diagram what it is, if it's positive or negative. So if we were calculating the x value, for example, you would determine that it would be the negative value because you're in quadrant 2 or 3, they'd be negative. And if it was the y value you were finding, in quadrant 2 would be positive, but in quadrant 3 and 4 down here, the y value would be negative. So if you're calculating that, just be careful with those signs. But for r, always positive, so the r value is 5. So now the question asks you to determine the 3 primary trig ratios. Now I've labeled the principal angle theta on the diagram. And if I did this question by trying to determine from those primary trig ratios sine of theta, well, that would be y over 5, or y over r, so that would be 3 over 5. If I did cosine of theta, that principal angle, well, that would be negative 4 over 5. And if I did tan of that principal angle, well, that would give me 3 over the y over the x, that would be 3 over negative 4. So if I took those and I tried to determine what theta was, what that would give me is that theta would be equal to the sine inverse of 3 over 5. And that would give me an answer, if I put that in my calculator, of 37 degrees. If I did cosine, though, and I determine what theta was from that, I'd get a different answer. I'd get negative cosine inverse of negative 4 over 5. I'm just cramming that in here for the sake of space. That would give me an angle of 143 degrees. A very different angle, wouldn't it? Now we can see from the diagram, that's actually the correct angle. But we just happen to get that with the cosine angle. If I did tan, I do the tan inverse of 3 over negative 4. Well, that gives me an angle of negative 37 degrees. And that would actually be an angle down here in this quadrant. Well, what one's correct? Well, we can see from the diagram it's the cosine angle, but we shouldn't have to figure out all 3 to determine what one's correct and have to kind of guess it based on the diagram. The better way to do this than this, so scratch that, the better way to do this is what I called using the related acute angle. And so using the related acute angle, if we set this up, this is going to be sine of beta. Well, the related acute angle is measured to the negative x-axis in this case. So sine of that related acute angle is the absolute value of y over the r. Well, that's 3 over 5. That's no different than what I had before. Cosine of beta, though, is different. Because if we take the absolute value of x over r, instead of being negative 4 over 5 that I had above, it's 4 over 5. And if I take tan of beta, well, that's the absolute value of y over the absolute value of x. So what that gives us is positive 3 over 4. They're all positive ratios. And so you might already think this because in the first quadrant, they would all be positive ratios, that this is going to give me the same angle each time. Well, let's actually solve these. In this case, beta would be equal to sine inverse of 3 over 5. Well, that gives me an angle of 37 degrees. Well, if I solve for beta in the second case, that would be cos inverse of 4 over 5. That also gives me an angle of 37 degrees. And if I did tan inverse, you guessed it, then that would give me an angle of 37 degrees. Well, you might think, well, that's a problem because it didn't give us the right answer at all. But what it gave us is it gave us consistency. So now we can apply the cast rule into the other quadrant. Because if possible, it's going to give you an angle between 0 and 90, which it does in all three of the cases here. So now for the last part where we determine what theta is, we can just say theta is equal to, well, this is going to be 180 degrees minus the related acute angle, 180 minus beta. Well, that's 180 degrees minus 37 degrees, which gives me an angle of 143 degrees. So my recommendation is always find the related acute angle first by making a positive ratio, and then interpret which quadrant it's in, rather than trying to figure out all your ratios and have to solve them all. Because in this case, if I just had sine, and I didn't have to actually use cosine and tan, it asked me to in part C here, but if it didn't ask me to use all three primary trig ratios, I could just determine it based on sine alone by just looking at what quadrant it's in. All right, here's the last example we'll look at today. Determine all possible values of theta if cosecant theta is negative 1.2. Well, the first thing to note here is that cosecant is 1 over sine. So 1 over sine theta is negative 1.2. If I rearrange that, that means that 1 over negative 1.2, I'm just swapping where those are, multiplying both sides by sine theta and dividing both sides by negative 1.2, I get sine theta is equal to 1 over negative 1.2. You might wonder, well, why do mathematicians do this? Well, they do that just to make things easier to write so they don't have to write a fraction. Really, that's really all it comes down to. So sine theta is equal to that. Well, if I try to determine what the related acute angle was, which I'm going to do here in a second, what I'm going to do is I'm going to start by saying sine of the related acute angle is going to be the positive ratio, so 1 over 1.2. And if I calculate what the related acute angle is, I take sine inverse of 1 over 1.2, and what I get is I get an angle of 56 degrees. 56 degrees. And so if beta is 56 degrees, that means that I have to consider not the first quadrant, because that's the related acute angle. I need to go back to this. Well, where is sine negative? That's what I'm asking. What quadrants is sine theta negative? Well, we know based on the cast rule, C-A-S-T, that sine is positive in quadrants 1 and 2. So that means it's negative in quadrants 3 and 4. And so what I'm going to do is I'm going to draw my related acute angle beta in both of these spots. So this could be 56 degrees here and 56 degrees over here. And then I'm going to calculate my principal angle, and there's two possible answers. So this is theta 1, and then theta 2 will be all the way around to there. And so for theta 1, that's going to be equal to 180 degrees plus the related acute angle. So that's 180 degrees plus 56 degrees, which gives me an angle of 236 degrees. And then for theta 2, I'm going to determine that by taking not 180, I'm going to take 360, and I'm going to subtract 56 degrees from that. 360 minus 56 degrees. And if I subtract 56 degrees from 360, I get the second angle of 304 degrees. So both of those answers, and you can go back and sub them in the equation. If you sub them back in that equation, cosecant theta, or even if you sub them into sine of theta, you're going to get the ratio of 1 over negative 1.2. They're both correct for that. Those are the two possible angles. There's always two for any angle or any ratio. You're going to get two possible angles. Hope that was helpful. Please like and subscribe. Thanks so much.